Okay, so looks like it's recording. I think that's fine. Here's where we were last time. Approximately, we were talking about differentiability. And again, there's this issue of, we can write down formulas for linear approximations where we, make baseless assumptions about partial derivatives and sort of arguing that, it ought to be a good approximation, right? That's all kind of wishful thinking until you know for sure that the function is sufficiently nice, that it's sufficiently regular, that these things that we feel ought to be good approximations actually are, right? And I gave you only the broad strokes of the justification for why we come up with this definition, but the definition is that we need for this expression to approach 0 as the point where you're evaluating the function, and the linear approximation approaches the point where you're doing the linear approximation. Pretty weird when you look at it in this form, but reminder, where it comes from, you trace it back, it's really just this thing called relative error. It's how far are you off compared to how far are you away from where you're doing the approximation, right? So relative, because you're dividing by that distance. And of course, error is this difference, and of course, the linear approximation is that those two terms there, and again, parentheses distribute the minus, etc. Okay, so it all kind of makes sense if you trace it back to its roots of relative error. Still, kind of a pain, right? And how do you do multivariable limits? We kind of skipped that part. And am I really going to have to write down this whole monstrosity every time? Oh my gosh, it seems like a lot of work, which makes us so thankful for this related idea of continuous differentiability. Because even though continuous differentiability, it is a slightly stronger condition. There are some functions that are differentiable that aren't continuously differentiable. So this is not a perfect solution to the problem. But good news, most functions that you're going to deal with in your day-to-day lives are continuously differentiable. And it's easy to check. You just have to look at the partial derivatives, confirm they exist, confirm that they're continuous. And again, continuous, we have these broad categories of functions that we know are continuous, like exponentials and polynomials and trig functions and logs where they're defined are continuous. And things like this. So mostly easy to check that something's continuously differentiable. And big theorem, if it is, if you can easily check that your function's continuously differentiable, then good news, it is also differentiable. And so we get this conclusion that otherwise, had we not had this wonderful notion of continuous differentiability, otherwise, this would have been hard to check, right? This is all the effort on the previous page. We'd have to deal with this nonsense, right? So, a big win that we have continuous differentiability. Okay. All right, so here's an example. Suppose somebody comes to you with this polynomial function here and says, is this differentiable? Right? So here's the argument we're going to make. First of all, we can compute the partials. In fact, you don't even really have to compute them. You can just note here that, this function's a polynomial, so the partials are all polynomials. It doesn't really matter what they are. Because, second fact, all polynomials are continuous. Again, the broad categories we already know, polynomials are all continuous. So, okay, that immediately means, by definition then, that this function is continuously differentiable. Which therefore means, by the above theorem, that yes, indeed, it is differentiable. So, there you go. Now, I do think this is a nice example, this argument that I have written down of something. You've heard me make this point a bunch of times. I'm sure this won't be my last. But you do have to show your work and explain your reasoning. This is an explain your reasoning kind of a problem. You'll notice that after the statement of the question, there's no algebra written. So it's not exactly that there's work to show, but there is, very importantly, reasoning to show. So, examples of where students can kind of gloss over critical reasoning is to say, for example, if students were to say all partials are polynomials and so it's continuously differentiable. Well, that is a true statement, but it leaves out part of the reasoning. The reason is that polynomials are continuous. And the fact that the partials are continuous, that's what gives you your continuous differentiability. Right? So very important, you need to actually say the word continuous in here before you draw this conclusion of continuous differentiability. Similarly, some students may write the partials are continuous and therefore it's differentiable. Well, again, it's a true statement, but it is not a complete line of reasoning, because continuous partials is not the definition of differentiability. It's the definition of continuous differentiability. So this really needs to get said. Right? So again, I remind you, it's not a question of whether the statements that you make are true. The fact that your statements are true is not sufficient. What we're looking for when we say explain your reasoning is that you explain why. We need to see this line of reasoning between your true statements. They need to kind of connect the dots, as it were. Okay. All right. So this is a good example to make that point. Okay. Now, here's another useful fact about differentiability. So, and we're not going to prove this. Yeah, question.
Can you just go back up?
Yeah.
Yeah, I just want to ask.
Yeah.
So, it's true that if it's continuously differentiable, then it's differentiable. But if it's differentiable, does it mean it's continuous?
Absolutely not. No, this is a one-way theorem. If you try to go the other direction, just not true. It is. There are counterexamples, and it's just not. There's some really interesting math in there. The nature of the counterexamples, and there are other ideas, sort of connected ideas, and it's beautiful math, and I'd love to talk about it, but it's not really what Math 219 is about. But yeah, so sadly though, one direction. Happily, it's the direction we need in practice most of the time. All right, good stuff. Okay, so another thing we're not going to prove, but I'm going to state and that you're welcome to use is that if you have a differentiable function, it's continuous. If your question is whether the function is differentiable, again, unfortunately, the arrow does not go both ways. The fact of a function being continuous does not make it differentiable. Right? But what we can do, a useful result we can pull out of this is to do what we call the contrapositive. Right? So the contrapositive is kind of the backwards phrasing of ultimately the same statement. So in this case, if a function is not continuous, well, then it's definitely not differentiable. And again, morally, that's kind of the same statement, because if you think about it, if a function's not continuous, well, how could it be? I mean, it can't be if it were differentiable, that would imply it was continuous, which it's not. And so therefore, that's not possible. So the function is not differentiable. So it's really kind of a, passive voice instead of active voice or something. It's really kind of a grammatical distinction more than anything else. In terms of meaning, they mean, well, pretty much exactly the same thing. So again, contrapositive is a great, really useful concept. And notice this gives us a differentiability test also. It gives us something that we can check for, that if it does come to pass, if the function in fact fails to be continuous, game over, we know the answer to the differentiability question. That function is not differentiable. Okay, so example. Y'all will remember this weirdo function from earlier. One of the first things we talked about in this subsection. And, at a glance, it's clearly not continuous. Look, there's great big gaps here, right? The function's defined to be 0 over here, but it's 1 up there. And there's this great big jump discontinuity. So it's very clearly not continuous. And therefore, it is not differentiable. Everybody good? Great. Okay, so now I'm just going to kind of develop some stuff we already have the tools of, but there's just certain perspectives I think are good to emphasize. So reminder that the DF matrix is the formula. It's doing all the heavy lifting in our formula for the linear approximation. So again, this is something we've already written down. Now that said, don't forget, one of the big ideas of a linear approximation is that its value is the same as that of the function at the point where you're doing the linear approximation. So I can rewrite that f as an L. Nothing really happened there. But what's nice about that is when I move this over to the other side of the equation, like so, right? Now I can reconceive of this left-hand side. This left-hand side now is literally the change between the points A and X. This is the change in our linear estimate of the values. And that's the very definition of what we call a differential. A differential is a linear estimate of a change. Right? It's not the actual change. The actual change is the increment. Again, not the same thing. Importantly different. The linear estimate of the change is the differential. And of course, the input change, also a differential. So what we see here is that this df, just one of the interpretations you can make, and I think this is a really good one and a really important one. df, this matrix, is a relationship between input changes and output changes. Right? I mean, this is what you multiply by the input differential to get the output differential. And, commonly sort of compactly written in this form right here. So df is the thing that you multiply by input changes to get output changes. Everybody on board? Everybody see what I'm talking about there? And you may recall at the very start of this chapter, right? Very start of this section, I guess it was, start of 2.3. We talked about fundamentally what a derivative is, and there's there's a bunch of different kinds of them, and but they do all have one big thing in common. What is the defining characteristic of any sort of a derivative? It relates input changes to output changes. So boom, and notice then that means that the derivative matrix. This is called the derivative matrix. It's really what we ought to call the derivative. I mean, this is the most general form of relating input changes to output changes directly. Vector valued, real valued, whatever. Right? Multivariable, all good. So very often we'll just call this the derivative. Just for the emphasis, sometimes we'll throw in that, by the way, it's the derivative matrix. Well, of course it is. That's what the derivative is. Right? And this is the weird thing about multivariable calculus. In single variable calculus, you get really used to the idea that a derivative is a number. Right? It always was. In single variable calculus, you can compute the derivative of the following function at a given point. Answer 3. Right? It's always a number. And fundamentally, it's just not what a derivative is. Again, fundamentally deep down, in a multivariable setting, derivatives are matrices. Because matrices are what you do to vectors to get other vectors. In general. Okay. All right. Now, of course, y'all recall that a matrix is a linear transformation, and so yes, we sometimes also call this the derivative transformation and view it as a linear transformation instead of as a matrix. But of course, in this Euclidean setting, they're kind of pretty much the same thing anyway. So this distinction is not critical, and the book mostly blurs this distinction, which I'm pretty comfortable with. So nothing to worry about there. But just other language to be on the lookout for. Heads up also, outside of the context of this class, DF will sometimes be written JF. J stands for Jacobian, which is a reference to a mathematician Jacobi. And so it just means the derivative matrix. That's all it is. Right? But it's a different notation and different terminology, so heads up for that. If you hear the Jacobian, they mean the derivative matrix. They mean this thing. Okay. All right. So here's a picture talking about what we're doing here. So again, keep in mind we have this function f, and f has a domain over here and target over here, and f takes a point A, for example, to its image point f of a. Let's say that point, for example. So f takes points in the domain to points in the target. Now let's look at our formula up here for what the derivative transformation does. Derivative matrix, aka derivative. That turns, let's see here, colored choices. I guess I'll just keep it green. That turns vectors, not points, but vectors representing differentials, representing changes. Not points, but movements of points, right, in the domain, and gives you vectors, aka movements of the outputs in the target. So the function takes points to points. The derivative takes input vectors to output vectors. So this is what the derivative matrix does. It takes this thing and it gives you that thing. Is everybody with me? Questions, feel free. Okay. All right. Okay. So now there's a little slick move that you can pull, and by the way, I'm sweeping formalities under the rug. This is not really what this course is about, but I'm going to say let's take this equation that we just had on the previous page, and let's just divide by dt. Right? And you just divide both sides by d. Let's not get bogged down in formalities, but if you do, then notice what you end up with is a different interpretation of the derivative matrix. The derivative matrix now you think of as something that relates not a discrete change in the input, but a rate of change, namely a velocity of the input, and relates it to, well, the velocity of the output. So, different interpretation, but morally equivalent. It still changes, it's just that they're instantaneous rates of change as opposed to discrete changes. Yeah?
Why wouldn't the output be acceleration?
What now?
Why wouldn't the output be acceleration?
Why would it be acceleration?
Looks like in single variable calculus, if you took the derivative velocity, it would be acceleration.
Oh, but see, now, I got you now. We're not taking the derivative of the velocity. What we're doing, this is the derivative of the function. And you just have to reinterpret what a derivative of a multivariable function is. We're not taking the derivative of x, and we're not taking the derivative of x prime. We're taking the derivative of f. So x is a function that describes, as I have it here, x is a function that describes location in this space. And in fact, if I were to draw the x function on this picture, I would kind of have to interpret it as, well, the xy plane is its output, and the domain is sort of the t-axis here. So here's the x function. And notice that's not what we're taking derivative of when we talk about that. When we talk about df, we're taking the derivative of this function, f, not that function, x. Does that make sense? Yeah. Yeah. No, it's a good question. I hadn't ever really thought of it, honestly. Yeah. Like, I see your point now. Okay. All right. Now, so, and by the way, so I made a statement some days ago. I lose track of time, but that, when you leave this course, I hope you don't leave this course thinking of the derivative as being, like what's your fundamental point of view about derivatives being partial derivatives. And I wonder, I hope that is more clear at this point now, that if you look back at partial derivatives, it's very myopic. It's, first of all, it's saying, I don't want to know about any other variables changing. We're just going to look at one variable at a time changing, and to the question of other variables changing, right? We're just ignoring that completely. And then furthermore, we're only looking at, let's say in the graph setting, we're only looking at it, therefore, a single cross-section of the function. So it's really very much like having blinders on. We're only looking the one way, right? So that's a nice tool and is useful in many ways. And even when I want to write down my more sophisticated thing here, when I want to write down my derivative matrix, you look back for the formula, it's written in terms of partial derivatives. Yeah, absolutely. So I like partial derivatives, but by themselves, individually, they're pretty narrowly scoped. That's not fundamentally what a derivative is. This is what I hope you will leave the course thinking of as being the derivative. It's the relationship between input changes and output changes in whatever form, be they discrete changes or rates of change, whichever, and correspondingly with the output. So this is the derivative. Partial derivatives are a nice little tool and all, but very limited. Yes.
Can you explain sort of geometrically, like, again, what A versus, like, the vector X, df are?
Yeah, that's right. So, okay, fair. So, X here, I'm talking about a point in the XY plane where I happen to be at the moment. But I also, coming down to here, I want to be able to think of X as something that's moving. Right? So imagine that this is the path that I'm following. And at a particular moment in time, X is at that point. But when it's at that point, it's also moving with a certain velocity. Right? And so X, think of X as kind of like a particle that's just kind of moving along in the XY plane. Does that make sense?
Yeah.
Yeah. Right. So X is momentarily at this point A, but it has a velocity which is something else. Yeah. Okay. All right. So now, the very first formula that we wrote down for linear approximations was for real valued functions. Let's see here. Yeah, okay, here we go. Real valued functions. We wrote down, I'm going to say morally equivalent to this formula. I've manipulated it in the same way that we did to get the formula above. I, moved the L to the other side and realize now that this too I can view as that's our change in our linear approximation. That is a differential. That's the output change. And this, likewise, is the change in the input. This is our dx, input change. And so the gradient, or you might say more specifically, dot product with the gradient, right, is, in this real valued case, the thing that relates input changes to output changes. And so some students find themselves sort of like, well, wait a minute, is it the derivative matrix or is it the gradient? Which is it? Right? Well, if you have a real valued function and therefore either of these is kind of on the table, I'm going to point out they're morally the same thing. So if you look at the derivative matrix for a real valued function, if it's real valued, there's only one output value. That means there's only one row in your matrix. And notice it is the row matrix consisting of, well, all the partials of F. By contrast, the gradient vector is a column vector consisting of all of the partial derivatives of F. It's the exact same entries. They're just kind of organized differently. Like the gradient is written vertically, and it's a vector, and you interpret as a vector, and you do vector algebra with it. The derivative matrix is written horizontally, and you interpret it as a matrix, and you do matrix algebra with it. But if you multiply it out, it's the exact same actual stuff, right? And whether you write it horizontally or whether you write it vertically, whether you view this as a dot product with a vector or a matrix product, I shouldn't put a thing there, matrix product with a matrix, it's still the same exact terms. And so it's actually, this is not actually a contrast. This is a sort of a notational alternative, really more than anything else. Just to have a picture, again, whether you call it gradient or whether you call it derivative matrix, it's a relationship between input changes and output changes that this, dot product with the gradient does. It relates the input velocity, for example, to the output velocity. So take your choice. Do you write it as dot with a gradient, or do you write it as a matrix df? In the real valued case, and of course that's the only one where we can talk about the gradient. Real valued only. Otherwise, you got to use the derivative matrix. Okay. So moving along, let's talk about higher order partials. There's a couple of things to say here. First, a kind of a linear algebra observation. So we've talked about the derivative matrix, the derivative transformation. Turns vectors into vectors, right? And it's linear. It's a linear transformation, aka a matrix, and so of course it's linear. All right. But now I want to talk about a different thing. Not the derivative matrix. A different kind of a function, a different sort of, we're going to take an input and produce an output, and it's going to be not df, it's going to be just d. Let's think about what d does. D is it's a process where I take as an input, I mean, what do I do d to? I do d to functions, right? I differentiate a function. So what goes into this d thing is a function. Well, of course, it's got to be a differentiable function, whatever. And then what comes out, what is the result when I take the derivative of a multivariable vector-valued function? Well, the result is the derivative matrix. In fact, let me go ahead and do this in purple. The same purple up here. The result is this derivative matrix, df, which itself you can think of as a function. Right? Anyway, make sure to distinguish between df, which is a matrix, and d, which is just the act of differentiation. The act of taking a function and producing from it a matrix by, writing down the formula for the derivative matrix. Okay, so when we say that differentiation is linear, we are talking about d. I don't know why my stylist wouldn't. Okay, there we go. We're talking about d. D is linear. df, of course, is linear. It's a matrix. D, though, much more substantial statement. D is also linear. So to flesh that fully out, when we say linear, right, linear means that if I have a linear combination of the inputs, so let's think about two functions, f and g. Notice f and g, they are functions. Here I'm taking a linear combination of inputs to the differentiation operator d. Linear combination of functions. Linearity means that the result is the same linear combination of the otherwise outputs, namely the otherwise derivative matrices. So you can take a linear combination of functions before you differentiate. You can take a linear combination of the derivatives after you've differentiated. Same thing, either way. That's what we mean by linearity of D. Is everybody on board? So let me flesh this out for you. I mean, it looks good on the page. Let's acknowledge that. I mean, when I write this down, it kind of looks like something that ought to be true, right? But that's a dangerous criterion. So let's flesh it out here, just as an example, so you can kind of see how this works. Here's a couple of multivariable vector valued functions. I can take their derivatives, partial derivatives, and keep in mind you got to organize them a certain way, etc. Right? So be careful with that. Now, on the other hand, I can also look at a linear combination of these functions. I can produce this thing called h, and you multiply it all out. You take that linear combination. Those are all arbitrary numbers, of course. But if you take that linear combination of these functions, you get this, which, of course, you can differentiate. Again, partial derivatives is all that's going on there, right? And again, you make sure you put the right partials in the right places. It's so easy to accidentally get these backwards. So easy to accidentally transpose your matrix. Heads up. Be very, very careful about that. If you get that wrong, things are going to go catastrophically badly. Okay, so did it work? Did linearity work as we expected? Well, here I'm taking a linear combination of the derivatives. Here I'm taking the derivative of the linear combination. And, well, okay, let's again think this through. This is a linear combination of the derivatives. that we computed up here. Right? Over here, I'm taking the derivative of the linear combination There's the linear combination, and here's the derivative. And again, if D were linear, if again, the question at hand here, did the linearity work? I need for these things to be the same, and this is just, again, some arithmetic you can do. But yes, these are the same. You just multiply out the linear combination there. Okay, that's pretty anticlimactic, I think. But anyway, it's important to make these fine distinctions on what we're actually saying when we talk about the linearity of differentiation. Okay. And now a reference. Again, I have to make tough choices, and I don't like to have to do this, but there is some stuff that I think doesn't quite make the cut in terms of being worth talking about in class time. But again, you're still responsible for it, so make sure you look at this. Is all in the book, but there's a product rule. Actually, kind of different product rules depending on whether vector valued or real valued or what kind of functions are you looking at there. And quotient rule, and of course it's all case dependent. So anyway, take a look at that. It's a lot of it is exactly what you would expect and hope to be true. And it is worth your time, I think, to crank out and confirm that, one or two of them, right? But anyway, this is all stuff that y'all can read in the book. Okay, higher order partials. This is somewhat analogous to single variable higher order partials. There are some important differences, but right off the bat, it's pretty much the same. I mean, if you have a single variable function of x, you can take the derivative. The result is another single variable function of x, and so you can take its derivative too. Right? So higher derivatives in single variable calculus is just, take the derivative of the derivative. No big deal. Well, same deal here, right? If you have a function of several variables, when you take its partial, the result is also a function of those same several variables. So let's see an example, see what I'm talking about here. If I look at this function here, it's a function of x and y. I can take its x partial, I can take its y partial, a little easy algebra there. And the results, note, also functions of x and y, just like f was. Right? So because those partials are functions of x and y, I can talk about, and let's take this one here, for example, let's take fx. I can talk about its x partial, or I can talk about its y partial, because it's a function of x and y. Now let's talk about the notation, and this is a little annoying, but some of this notation is a little uncomfortable, but it's just notation, so don't worry about it. It's just the notation. Let's write down this thing, though. So here we've got the partial of f with respect to x. And what I'm going to do to it is I'm going to take the y partial. And so if I were to just write it down sort of naively, just kind of blindly, taking the y partial of the x partial should look like that. And the reasoning goes, I think, let's see, I've got a dx here, so I'll put that there. And I've got a dy there. I'll put that there. It's just kind of you can sort of see what happened there. It just seems like this is a reasonable sort of compact shorthand representing the action of what happened here. Everybody buy it? I mean, this used to bug me because I'm like, wait a minute, am I multiplying partial by partial? No. It's just, it's there twice, and so they call it partial squared. So anyway, apologies for the awkwardness there. Likewise over here, if you're taking the x partial of the x partial, it's it's kind of exactly what you would sort of sloppily want to call it. Okay. All right. Oh, now other thing I should point out though, if we're taking the x partial and doing the y partial of it, look at what that looks like if I write it down in sort of the Newton-like notation there, right? Y partial of the x partial. Notice that the orange is kind of on the right-hand side if you write it in Newton notation, and it's kind of on the left-hand side if you write it in sort of Leibniz notation, right? So, sadly, in the same way that, I sort of feel like this has to be abbreviated with the y partial on the left in the denominator, the y partial kind of has to likewise be sort of on the right in the subscript with this notation. It's very frustrating. But anyway, it's just a notational point. Heads up, right? Be on the lookout for that issue. Okay, likewise, we could have taken the y partial and asked about what is for example, the x partial of that, and the notations that we would choose for that, likewise, totally analogous, like this over here. Okay, is everybody on board with the notation? All right. Okay, now, check this out. Look at this. How weird. The y partial of the x partial and the x partial of the y partial ended up being equal. And that, weird, right? What are the odds? Turns out odds are pretty good. This is not a coincidence. In fact, I don't want to say it's certainly not always, but in terms of everyday experience, I'm going to say usually this is true. Usually, it doesn't matter which order you do your partials. Now, in order to make that precise, I need to pause. We're going to put a pin in this. I'm going to define a new object. I'm going to define a thing called CK. This is pretty standard notation. It gets used a lot. It's very convenient. It's just referring to a category of functions. So CK, here when I highlight this better, CK is a collection of all functions whose kth order partials exist and are continuous. So the C is for continuous, the K is for how many partials have to, in fact, be continuous. All right? Everybody okay with that? Again, it's just notation and terminology. So that said, if you're talking about a function that is in this category, then as long as you're taking the same number of partials, let's see, let me do it like this. As long as the number of partials you're taking is the same as that k, then all the mixed partials are indeed equal. In other words, you can rearrange what order you're taking the partials all you want, and it's fine. It won't make any difference. Switch around the order of the partials however you like. Now, the way I wrote this down here is, it's a little notation heavy, a little bit clunky, but notice what I have written here, that these lists of I'm doing, if you will, this list tells you the order that I'm doing the x partials on the left side, and this list says what order am I doing the partials on the right side. All I'm saying is that these are rearrangements of each other, and rearrangements just means it's the same set, just moved around in terms of which one's first, second, third. Okay. All right. Okay. Now, what does this look like geometrically? And again, if you have an algebraic thing, it's very, very helpful, if not essential, to know what it looks like geometrically so that you can kind of relate it to things that you might be doing business with. What's the point of taking a second partial if you don't know what it means? Right? You can talk about it, but if it never connects to anything real, then who cares? Right? Okay. So again, I'm going to focus on the graph setting, right, where really the best answers are. So in this graph setting, let's start with fxx. What does fxx look like geometrically? Now, let's think through the process. How would I compute fxx? Step 1 for computing fxx, I've got to recognize that x, for this first partial derivative, is my variable. That means that y is going to be constant. If y is constant, then that means that I'm looking in this half plane where this cross-section plane where y is a constant, and that means that I am looking at as I move in the x direction, and we know slope and all that business. But after I've taken that x partial, then I need to now take the x partial again, which means I will just continue to keep looking in this same cross-section plane that I was already looking in. So, good news, if you're taking the x partial of the x partial, you're just setting y equal to a constant and keeping it constant. In other words, you're turning your multivariable function into a single variable function, and then just taking the good old regular old Math 111L second derivative with respect to x. And second derivative tells you concavity. And so the fact that this cross section is concave down, as I have it drawn in this example, concave down is the indication of fxx being negative. So if I had a formula for this Pringle, the x second partial would be negative at that point. Is everybody good? Okay. All right, analogous argument can be made about fyy. Again, you think it through when you're taking fyy. Well, the first thing we have to do in taking the y partial, that first y partial, is set x equal to a constant. We'll be looking in that cross section being, that curve. And then we're going to continue to keep x constant. In other words, at the start we keep x constant, we set it constant, we keep it constant, and then we take the y partial of the y, we take the y derivative of the y derivative. It's just a second derivative. Again, it stays a single variable function where y continues to be the only variable throughout both processes. So again, as I have it drawn here, the Pringle is concave up at that point, and concave up means positive. So, nice interpretations for these what we call unmixed partials. So fxx, fyy, interpreted on the graph setting. It's I'm going to say kind of exactly what you would hope it would be. Okay. Now here's where it gets tricky, though. What if I want to talk about what we call a mixed partial? What if I want the x partial of the y partial? This gets weird because y is a variable for the purposes of the first part of the calculation. But then y becomes a constant for the second part of the calculation. So I can't just say, oh yeah, it's a single variable function. X is always a constant. No, it isn't. Or y is always a constant. No, it isn't. So we're going to have to deal with this in a more careful way, and here's the way that makes sense, at least as I see it. First thing we're going to do is we're going to make an interpretation of the y partial, and one of our very convenient interpretations of a y partial is that it is the slope of the tangent line in the y direction. So okay, let's be careful about this. Here's a point in my domain. And y partial, we're going to look in the y direction, right? And as I look in the y direction, I didn't draw a surface here because the picture would get all muddly and hard to interpret. But as I go in the y direction, there's going to be some sort of a cross section to the surface, and that cross section is going to have a certain kind of a slope. And we're going to imagine the slope, but I'm going to draw the tangent line only. Okay, so this is a kind of a picture of the y partial, as it were. Next question, how am I going to interpret on this picture the x partial? Okay, we're going to now sort of take a different point of view. We're not going to understand this x partial in terms of slopes in the x direction. Very importantly, because the thing I'm taking the x partial of isn't f. I'm taking the x partial of this other thing. Now, if I wanted to interpret this x partial, if I wanted to interpret this x partial as a slope, I would need to have a graph of the thing I'm taking the x partial of. I don't have a graph of the partial of f with respect to y. I know. I have a graph of f. This y partial, I don't have a graph of it, so I can't talk about the slope of that y partial. What I can do is think of the x partial in terms of, okay, well, yeah, but it's a measurement of how things change as I move in that x direction, right? So I can talk about and draw pictures of this process of moving in the x direction. And now let's just think about then, as I move in that x direction, how do these y partials, namely slopes as I'm moving in the y direction, how do those y partials change as I move in the x direction? And I just, again, drew an example just so I could have something to talk about, but maybe these are the tangent lines at these different points. And let's think about what's happening as I do this, as I go through this process. Well, over there, the y partials are pretty steep negative. And then over here, still negative. And over here, sort of gently negative. And then here, it looks like it's about 0. And then here, it's actually starting to look kind of positive there. So in this process, as I am moving in the x direction, the y partials are increasing. The thing I'm taking the x partial of is increasing as I move in the x direction. So in this case, this x partial of this y partial would be positive. Does that make sense? It's pretty geometrically challenging, right, to sort of visualize this. But now I'm going to make another appeal here as to, what does this look like? What do you all see when you see this? And keep in mind, these are all supposed to be tangent lines to a surface that I haven't drawn. Well, what I see, and I've never been able to figure out a visual aid that I can use. I kind of wish I had like a sheet of rubber. Like a paper doesn't do what I need it to do, but if I had a sheet of rubber, you could imagine grabbing it on the corners and kind of twisting it like this. Twisting it kind of what you might call clockwise on the back, but then kind of counterclockwise on the front. And that twist would produce cross sections that do look kind of like that. So this is our answer. This is the interpretation that we make. When you look at a second partial, a mixed second partial, it's in a way it's indicative of this kind of a twisting of the graph, and the name they give this is called torsion. But that's, you don't need to worry about that. But anyway, that's geometrically what that mixed second partial looks like. Okay. All right. Okay, let's see. How are we doing on... Oh, I'm almost out of time. Okay, well, let's see here. All right, I tell you what. We'll pretty much just go ahead and draw the line there. I'm pretty sure I owe y'all 45 seconds anyway. So we'll call it... It's Friday morning, so we'll go ahead and call it now. See y'all later. Hope everybody enjoys the game, and I'll see y'all on Monday.